Hello students, welcome once again to CHEM is Try. Today we want to consider the second and the third uses of standard electrode potential values. In our previous video, we spoke about the first use of the standard electrode potential values. Over there, we were made to understand that always the standard electrode potentials of half cells given to us are written as standard reduction potentials. And we said that we can use the standard reduction potential values to calculate the whole EMF of a galvanic or a voltaic cell. I hope you remember the formula. The formula was standard electrode potential of the cell is equal to the standard reduction potential of the cathode minus the standard reduction potential of the anode. That is what we learned in our previous video. Today we want to talk about another important use of the standard electrode potential values, which is it can be used to predict whether a reaction would be spontaneous or not. Remember, in a galvanic cell, the reaction is supposed to happen on its own, so it is said to be spontaneous. So whether or not a reaction can form a galvanic cell can be deduced using the standard electrode potential values. But how? When we use the standard electrode potential values to calculate the total EMF of the cell and we get a positive number, it tells us that the reaction would be spontaneous and it will occur as it's supposed to be in a galvanic cell. However, if we calculate the total EMF of the cell and we get a negative value, that means that reaction is not spontaneous. And if it is not spontaneous, the reverse of that reaction has to happen. The cathode will then have to become the anode, and the anode will have to become the cathode. Let's look at these examples and see how we can use the standard electrode potential values to predict whether or not a reaction will be feasible. In this example, we are being asked to predict whether the following reactions would be spontaneous or not. In the first reaction, we have the reaction given to us in the cell notation form. Cell notation form. And in our second example, we have been given the actual chemical equation. So we'll be looking at how we are going to find out whether the reaction will be spontaneous or not using the cell notation form given to us. And we will learn how to do that using the actual chemical equation. Let's start with the first one. Remember we said when we are writing the cell notation, we first write the oxidation reaction. Then we will bring our salt bridge. Then we will write our reduction reaction. And what did we say about oxidation and reduction? And ox and red cat. Which means our oxidation reaction is going to constitute our anodic reaction. Then the reduction reaction is going to constitute our cathodic reaction. So over here, this question is trying to tell us that copper half cell is the anode. Copper half cell is the anode, and the iron half cell is the cathode. That is what this reaction is supposed to be right now, as it is over here. But we have been given the standard reduction potential values of the copper half cell and the iron half cell. So how are we going to use these values to predict whether this reaction will be spontaneous or not? When given such a question, the first thing you do is you calculate the total EMF of the cell. And to do that, you need to know the cathodic reaction and the anodic reaction. And now, as we have identified the cathodic and the anodic reaction, let's try and use that piece of information to calculate the EMF of the whole setup over here. The EMF of the cell is giving us the standard reduction potential of the cathode minus the standard reduction potential of the anode. And we have been given the cathode as the iron half cell, and its standard reduction potential was given in the question as negative 0.44 volts, negative 0.44, minus the standard reduction potential of the anode, which is our copper half cell, which we were given as positive 0.34 volts. This should give us negative 0.78 volts. What did we say about getting negative value as our EMF of the cell? We said if our EMF of the cell is negative, it tells us the reaction will not be spontaneous. So this half cell, this electrochemical cell would not be spontaneous. All because the total EMF of this galvanic cell is going to be a negative value. And if it's going to be a negative value, that means copper cannot serve as the anode, whilst the iron serves as the cathode in this galvanic cell. It wouldn't happen. We have to switch for the iron to rather become the anode and the copper to become the cathode if we want this reaction to proceed. So this reaction would not be spontaneous. Let's look at the second one. In the second example, we have a chemical equation given to us. From this chemical equation, we can see that tin has oxidation number of 0 as it is an element on its own. Beryllium is a simple ion, so its oxidation number is equal to its charge. Tin 2 plus is a simple ion, so the oxidation number will be equal to its charge. And beryllium is an element standing there alone, so 0. So from tin to tin 2, we are experiencing an increase in oxidation number, and that means it's an oxidation reaction. From tin with oxidation number of 0 to tin 2 with an oxidation number of positive 2, we are experiencing an increase in oxidation number. So this one is called the oxidation half reaction. And what did we say about oxidation? We call it the anode. Then we have beryllium. Its oxidation number reduced from positive 2 to 0. So it is undergoing reduction. And what did we call the reduction half cell? The cathode. So from this equation, we've deduced what our anode is and what our cathode is. Our EMF of this cell will be equal to the standard reduction potential of the cathode minus the standard reduction potential of the anode. In the question, we were given the standard reduction potential of tin to be negative 0.14, and that is constituting our anode, and that of beryllium to be negative 1.99, that constitutes our cathode. So negative 1.99 minus negative 0.14. So we are going to have negative 1.99 minus negative 0.14. And that should give us negative 1.85 volts. Once again, we can see that our EMF of the whole cell is giving us a negative value. this goes ahead to tell us that this galvanic cell will also not be spontaneous. What it means is that when tin meets beryllium ion, there is no way tin can give its electrons to the beryllium ion. Rather, it has to be the beryllium element meeting the tin 2. Then the tin 2 ion will accept electrons from the beryllium. So beryllium will have to now give electrons to tin. So it is the reverse of the equation that will be spontaneous. But the forward reaction is not going to be spontaneous. And the question we're giving the forward reaction. That tells us that since the EMF of the cell is negative 1.85 volts, it's negative. So the forward reaction will not be spontaneous. Now let's go and look at the third use of the standard electrode potential values. The standard electrode potential values can also be used to predict the standard electrode potential of unknown couples. In this instance, we have an element whose standard reduction potential is already known. Then there's another different element whose standard reduction potential value we have no idea what it is. Well, we could send that substance to the SHE for us to find its standard reduction potential value. But what if we don't have the SHE? We could couple that half cell to another half cell whose standard electrode potential is already known. After connecting that cells, after connecting those two compartments together, we would record a total EMF of that whole setup. Then, with the knowledge of that total EMF and the standard electrode potential of the element which we already know, we can calculate the standard electrode potential of the unknown. This is what we mean. In this example, we have a reaction below. Zinc combining with X2 plus to form zinc 2 plus plus X. That is our reaction. And when we connected the zinc half cell to the X half cell, we had a total EMF of positive 1.88 volts. But we already know from the standard hydrogen electrode that when we compare zinc to that electrode, we are supposed to get a standard electrode potential value of negative 0.76 volts for zinc. So that one is already known. It is in literature. And in one of our videos we've done already, we gave that chart. So we already know that of zinc to be negative 0.76 volts. So knowing this and the total EMF of the cell, we can calculate the standard reduction potential value of the X couple. How are we going to do that? Before we do that, we have to look at the equation we have been given and analyze it critically to see which substance is undergoing oxidation and which substance is undergoing reduction. The one undergoing the oxidation will be named as our anode, and the one undergoing reduction will be named as our cathode. Then we use our original formula. E naught of the cell is equal to E naught of the cathode minus the E naught of the anode. Then we look for the electrode potential value of that unknown couple. So right now we don't know, unless we consider the equation to see which substance is undergoing oxidation and which one is undergoing reduction. So let's put down our equation once again. Zinc is an element on its own. So its oxidation number is 0. X2 plus is a simple ion, so its oxidation number is equal to its charge plus 2. Zn2 plus is also a simple ion, so its oxidation number is equal to its charge plus 2. Then X is an element standing there alone, so its oxidation number is equal to 0. Comparing these oxidation numbers, when we consider zinc, you realize that zinc has its oxidation number increasing from 0 to positive 2. So it is undergoing oxidation. Then we said the part of the cell where oxidation occurs is called the anode, anox. Then you can see that X has its oxidation number decreasing from positive 2 to 0. So it is undergoing reduction. And what did we call the reduction half cell? The cathode. So if I identified our anode and our cathode, that is the most important aspect of that question. So let's try and put down our formula and insert our standard electrode potential values in the formula. So the EMF of the cell is given as the standard reduction potential value of the cathode minus the standard reduction potential value of the anode. And we have been given the EMF of the cell to be positive 1.88 volts. Our cathode is supposed to be the X couple, whose standard reduction potential value we don't know, and it is what we are looking for. But our anode is our zinc half cell, and we have been given its standard reduction potential value as negative 0.76 volts. So this becomes 1.88 is equal to the reduction potential value of the cathode plus 0.76. So we move this one here, then we get 1.88 minus 0.76. That will give us 1.12 volts, positive 1.12 volts. So with knowledge of the EMF of the cell and the standard reduction potential value of one of the species, we have been able to calculate the standard reduction potential of an unknown couple. So X2 plus X, its standard reduction potential value is equal to positive 1.12 volts. Another important use of this standard electrode potential values is to help us create that chart, the electrochemical series. And that series helps us to identify which substance is a very good oxidizing agent and which substance is also a very bad oxidizing agent. It helps us also to see which substance is the strongest reducing agent and which one is the weakest reducing agent. So these are the uses of the standard electrode potential values. Now that we are done with the galvanic cell, let's go into the past question. Let's pick one question from the past school and let's see if we can combine all the things we have talked about concerning galvanic cells to help us solve such questions. I have only one question today, and in our next video, we'll be considering that question. Thank you.